So in this new project, what we will try is to understand the process of angular estimation. So let's start with simulated data, and then we will move to this other branch where we have experimental data. So the main idea in this project is that when we have to estimate the orientation of each one of the particles, because of the noise, we will have estimation errors. So let's start with a structure that is a atomic structure. It is this 1NZO. So this is I have it here. So it is the crystal structure of wild-type penicillin binding protein 5 from Escherichia coli. Okay, so it is some structure, and we can see how it looks like in our setup. So we have 1 angstrom per 0.5 angstrom per pixel, and it has 40 kilodalton. So actually the size, whether it is 40 kilodaltons or 100 kilodalton, in experimental data it matters, because at the end alignability is a matter of signal to noise ratio. So if you have a lot of signal, it will be easier to align, and if you don't have so much signal, it will be much more difficult to align. So this is how slices look like of an atomic model that is converted to Coulomb potential. So here we see the different atoms, and we can also see it in 3D and see how it looks like. So yeah, so it looks like this, and here we see all the details of the structure. Okay, so we generate projections from this structure in all possible directions. So let us look at the projections, and also, so this is these are all possible directions. So you see here the projection sphere, and you see a point for every projection, and then we see that we are fully covering the sphere. And then also we can see the projections. We can check that, for instance, here. Later, when we introduce the CDF, we will see that this extra space around is important. So yeah, so we see all possible projections of this structure, and this is how a clean projection looks like. Okay, so now just to make sure that what is the limitation that we would have by reconstructing such a clean data. So we can see that the structure, so these 40,000 images are with perfect angles. They're good enough to reconstruct almost perfectly the original structure. Okay, so now let's add noise. So when we add noise to the particles, they don't any longer, we see the particle in the middle, but we don't see the details. So this lack of details will be what prevents the angular assignment from being perfect. So now we will do a few things. So the first thing will be to split this data set in two halves with perfect angles, make a couple of reconstructions, and compute the resolution with perfect angles. And these resolutions will be limited by noise. So this is how a reconstruction looks like without any filtering. So normally the reconstructions we see, they are heavily filtered, so that we remove the noise around. So but the raw reconstruction looks like this, and this is somehow the limitation that we have obtained by having noise in our structure, but just gray noise, not noise in the angles. And then if we compare the resolution of these two, then we see that the resolution is 3.4 angstroms at this FSC 0.14, and then we can add the two volumes, filter at 3.4 angstroms, and this is now this is how we are used to look at our structures. So we estimate what is the resolution of our structures, and then we filter at that resolution, and you can see the difference between these slides and the corresponding slides in any one of the individual reconstructions alone. So this was a slide 147, so we can go to the same slides and we can compare this one to this one. So you see one is much cleaner than the other, but this information was contained here, so even if it is hidden by the level of noise, after filtering we can recover it. Okay, so this is one idea, and then for instance we can compare this structure or this structure that was adding the two to the perfect PDB. This one has noise, so just a reminder, it has half the noise than the other because we have average a couple of structures, and we can compare this structure to the original PDB. And now the correct threshold is 0.5. So when you compare one noise structure to a clean structure, this is the PDB. The PDB is clean. So when you compare these two, the FSC is 0.5. When you compare two noisy structures that are computed from two halves of the data, the threshold is this 0.14. Okay, so we see that the 0.5 threshold, this 3.4 angstroms, is the same as the one that we have obtained here, 3.4. So this is just a measure of consistency and understanding how the FSC measurements work. Okay, so now we have these particles. So on one side we have used the perfect angles because we know them, and we see that by noise we are limited to 3.4 angstroms resolution. Now we do an auto refine of Reliant, and here I want to say that this is not any statement against Reliant or in favor of Reliant. It is just okay, so let's use an algorithm to estimate the angles, and we will estimate the angles filtering the structure at 60 angstroms. That is the standard one, or one of the common actions we do, and then we get an FSC that is consistent up to 3 angstroms, and we can compare. So let's look at the structure. So the structure looks good. So it basically has no noise in the background. So we see that we have fluctuations, but they are very small compared to the signal. So this is what we should expect if we don't have any disturbance around. So 40,000 particles should give something like this if we are perfectly capable of aligning them, not perfectly, but we will see now, but decent alignment and no noise around, perfect CDF correction. If our structures, they don't look like this, then that means that we have some problems in any one of these steps. Okay, then we can align, because the particle, the orientation of the 3D reconstruction may drift over the iterations. We can align this reconstructed volume to the original one. This is the PDB, and now we can compare the angles that we simulated with the angles that we have estimated. So we have, for that, we have this analysis tool, and now we can, for instance, show the angular difference. So the angular difference is the average in the three axes, x, y, z, of the orientation between two sets. So the first one was the perfect orientation, the second one is the estimated orientation, and we can see that for many particles this difference is small. We are in the at the level of 1 degree, 1.5, 2, this is 2 point something, 2.5, but then for a few particles we are we have very large errors. Okay, so this is the first message. So even if you have very good setup with no particles around, no CDF, just noise, and it is not a terrible noise even in this case, there will be a fraction of particles for which you will have mistakes, and for the big mistakes, and for the other particles the angular assignment will not be perfect. It is good enough to have a good reconstruction. So we have two kind of errors, small ones and small ones sufficiently close to zero, and the average is not zero, so it is this is a mistake. If we are close to zero, but even the average is zero, but having an angular error that is around zero, what makes this a blurring, it doesn't cancel out to produce the perfect structure. That is one thing. The other part of the message is that for a fraction of particles we will make big mistakes. Okay, even in perfect conditions. So that is one thing. We can also, for instance, sort by the shift difference, and in the shift difference we see the same kind of pattern. So small errors for many particles, and then big mistakes or bigger mistakes for the others. And again, this is just blurring. So we have a fraction of the particles that are contributing with very little blurring, and another fraction of the particles that are contributing with much larger blurring. We wonder, so now we will not go anymore to this detailed analysis, so we can look at kind of summary here. So the average angular distance is 1.3 degrees, and the global shift distance is 0.35 pixels. So now we wonder whether this accuracy is caused by filtering at 60 angstroms. So we filter much less our map now at 8 angstroms, and again we repeat the same analysis. So the FSC, you see that this didn't change, the one estimated by Rely-On, and we know that this has to be an overestimate, because with perfect angles we have a resolution of 3.4 angstroms, and here if you have mistakes, it cannot be that the resolution is better than 3.4 angstroms. So it is already an overestimate of what is the true resolution here. So the other one is that okay, so if now we compare the angles, it is in the same kind of values. So 1.36, this one was 1.32, so same kind of angular errors and global shifts. So in this particular case, it didn't depend on how much you had filtered your initial map. It may depend, so depending on the data set it may depend, but it may also not depend on it. So it depends on what is the landscape of this goal function that we are optimizing, and how we are traveling in that goal function. And here what we wonder is what about the stability of this assignment. So let's say that I repeat it twice. So should I get twice the same result exactly? These algorithms are not deterministic. They normally have a random initialization, so we know that we will not have exactly the same solution, but okay, so now we can compare these two, so one and its repetition, and now we align these two sets, and we see that we have the same kind of errors as we had before, same kind. So we can also for instance make the same kind of plots that we did before. So here same kind of angular errors, and the same for the shifts, so we can do it also for the shifts. So now we sort by these, we plot, and same kind of stuff. So that means that this behavior is something intrinsic to the uncertainty caused by the noise in the particles. So you have noise in the particles, and that will cause an uncertainty in the angular estimation, and that is very interesting to know. Okay, so what about if we do it now with real data? So if we do it with real data, I have taken this Empire dataset. I have opened it here. So this Empire dataset is substance P neurokinin receptor G protein complexes. Okay, so whatever they are membrane proteins, and this is the protein. We don't see here the membrane, but it is there. We will see it now in the structure. So these are the micrographs. This is the particle corresponding to the data set that we have selected. There are 3 data sets here, and we have selected one of them. Okay, so now we come to here. These people have deposited the particles and the angles that they used for reconstructing, and so first verification that we can do is just to reconstruct using these angles to make sure that we can recover the structure that they also reconstructed. And we see that okay, so for instance here we see same kind of background, relatively clean without any artifact, and then the structure in the middle corrupted by this noise. And we can also look at it in Chimera. We will see now first all these small points around are caused by the noise, and then we can get in. Here we have the so here we have this membrane in which the particles are embedded. You see it here. So here you see this is the membrane, part of the membrane that they kept with the particle so that the transmembrane region could be preserved. Okay, so here we have our structure. You can this is just for representation. You can hide the dust of this structure, and then small points will be deleted, small points of size, this amount of voxels. Okay, so so here we have our structure, and depending on the threshold we can see better or not. For instance, the transmembrane region, we see very nice alpha helices here. Okay, so this is our structure, and now we can estimate the angles twice with ReLiON. I did it once with CryoSpark, and the different resolutions claimed by each one of them. This one claimed at the beginning in their structure they claimed, I don't know, 3.2 angstroms, and here we have got 4.6, 4.7 and 3.0. So another message here. So do not trust blindly these numbers. We will see again along the course that these numbers are indicators of the quality of your structure, but they are not the absolute truth that you have to blindly believe. Okay, so always look at the structure. So we will look at the structure at different, for instance here, and here we can look also at the structure, and again, this is not any claim that CryoSpark is always better than Relion or anything of the sort. Okay, so let's go to the same slice. So we can open this one, we can open this one, and in this case the resolution, a better resolution, a better number actually means a better appearing structure. So here we see more details than in this one. How much more details? Somehow it is indicated by this resolution increase from 4.7 to 3, but doesn't mean that we see we should believe these 3 blindly. Okay, so better resolution means probably better quality. What is the exact quality is a different stuff. Okay, so yeah, so let's look at now the same kind of comparisons that we did before. Now we can do many more. So we can see, for instance, what is the Relion stability. So if we measure it twice, what is the kind of uncertainty that we have? So now we have 4 angstrom, 4 degrees in uncertainty, and almost a pixel. And again, we can look at these results, and we will always have the same kind of behavior. So a small or a fraction of the particles for which we have small errors, and then another fraction of the particles for which we have larger errors. And how small, how this fraction goes depends on the data set. So for instance, we can look go to the very end to see what kind of particles we have big errors. And for instance here, it is hard to see, but here I would say the particle is pretty off-centered, so that's why we have so different estimations. Here it seems to be very defocused or in the middle of nowhere. I don't see the particle well there, and here again it could be in the middle of nowhere. So and we have the same kind of behavior also for the shift. So now we can do the shift analysis, and same kind of stuff. And here it is a relatively well behaved example, in the sense that the fraction of well aligned particles with small errors is relatively large, or it is almost 95% of the particles are well aligned. We will see many other examples in which this is not so well behaved. Still, we can compare which is the fraction of particles, so that we can look at here. So what is the fraction of particles whose shift difference and angular difference compared to the ones at the EMDB? This is not EMDB, this is the Relion stability. So how many particles are assigned within 1 degree and 1 pixel? And we see that there are not so many, so very small fraction. So about 5% of the data or 6% of the data has this very accurate assignment. If you relax it a little bit, so for instance this is about a third of the data, 33% of the data get something that is within two pixels and 2 angstroms. But the other 2/3 of the data, they get larger errors. So again, this idea that when you estimate the angles, there will be an associated uncertainty caused by the noise. We can compare Reliant with the original assignment, and we see that now the differences are much bigger. So this is again another message. So depending on it is not enough to say I have computed this with Reliant. It also, the angular assignment and all the analysis and all the results depend on how you have used Reliant, which are the parameters that you have used, and that is why it is so important to disclose everything that you have done. So you see that if you run Reliant twice, you get a much better stability than if you compare Reliant to whatever was done before. So it doesn't mean that the current Reliant estimation is better than the other one. I don't claim that. Probably based on the resolution, that is true. So the previous, or that is the opposite. The previous one was better than the one we have estimated now. So again, the same message. Having a very good result depends on spending a lot of time on the data, making sure that you do a lot of good choices. You choose the particles that are stably aligned, that are that you are sure that the angular assignment is the right one. And for that, a simple processing, this fast food idea of making it quick, it doesn't go really. Okay, and now we can estimate, for instance, this is CryoSpark. We can compare CryoSpark to the EMDB, and here we see that it is more similar, but it's still within the range of this uncertainty that we have because of the noise. And also we can compare how many particles share the same alignment within 1 degree and 1 pixel, so not so many with the EMDB and Reliant, and a little bit more with 2 pixels to degrees. And here there is a big change from this one to this one, and probably the reason was that this angular assignment was done with CryoSpark, maybe. Okay, so yeah, but even CryoSpark with itself doesn't agree so much, so it is not 100% of agreement. So that depends on what is the what are your parameters, what are your choices, your particular choices. So as a summary of this project, so angular estimation, because of the noise, you will have uncertainty, and then this uncertainty can be taken care of by comparing different estimates of the same angular assignment. So because the algorithms are not deterministic, you will have slightly different results every time, and then the ones you will have two kind of errors, small ones and big ones. And small ones blur a little bit your structure, they are not terrible. The big ones, they are corrupting your structure, so you are putting something that is completely wrong on top of your structure. The fraction between small errors and big errors will make whether this corruption is catastrophic or not. So with this we finish this project, and see you in the next one.